Let's use polar coordinates to compute an area enclosed by a four-petal rose. Now, back in Calculus 2, we talked about some polar coordinates, and we referred to this particular equation as the rose equation. That is, r is equal to 3 cosine 2 theta. And when the coefficient of theta was an even natural number, then that would give us the number of actual petals. The petals in this case would be 2 times 2, which is 4. But you don't have to remember that. Few students do. What we can do is analyze this equation as a Cartesian equation and then rewrite it in terms of a polar equation. So here we'll think of theta as independent and r as dependent. So this is just a basic trig curve. We see the period here is pi. And so I've written out 2 periods here, just using the principal points of the cosine curve. Obviously the amplitude is 3. Now what we're interested in doing is taking this curve and translating it to a polar curve. Now what we see here, this gives us the actual values of r. So when theta is equal to 0 radians, we have r equal to 3, which we have here. And then when theta is equal to pi over 4, r is 0. So we have our pi over 4 measure here, and theta is actually 0. So for this part of the curve here, we map out this piece of one of the petals. And that's all we need, because as we continue to move around, as we go back through these numbers here on the x-axis to 2 pi, we complete the circuit. So we actually get 4 petals, and then as we continue on again, we just trace the curve again. Now, because of the symmetry, we don't have to work very hard. That's why I highlighted theta equals 0 and theta equal pi over 4. So we can look at this area here represented in the polar representation. That is, theta will run from 0 to pi over 4, and then r will run from 0 to 3 cosine 2 theta. And that will be our representation of this area here. That is 1/8 of the area enclosed by the four-petal rose. So what we will do is define area to be 8 times the double integral of the area element over the region r. Now, of course, this is in terms of polar coordinates, so our area element is the rd theta. So that's the first translation we make. And then, of course, we need to change our limits to respect our representation here. That is 0 to pi over 4 and 0 to 3 cosine 2 theta. Now we have a fairly straightforward integral. So at this point, add 1 divided by the new power, we get r squared over 2. And then, of course, we can factor to get 8 over 2. And then, of course, the lower limit gives us nothing but 0, but the upper limit will give us a 9 cosine squared 2 theta, which we have here. So now again, we can factor, if you will, the 9. We've got a 4 here. 4 times 9 is 36. And then, of course, we replace the cosine squared with the power reducing formula, 1 plus cosine 4 theta divided by 2. Now we can break this up into 2 integrals. So we'll have 36 divided by 2, which is 18, d theta, 0 to pi over 4. And then, of course, here, we're going to need to adjust this by the chain rule. We need a 4 d theta here, but we don't have it. We just have a d theta, so we will compensate with a 1/4 by the 18. And then, of course, we'll just integrate cosine 4 theta from 0 to pi over 4. The antiderivative of the cosine is the sine, so that gives us this particular expression. And then, of course, this integral is just 18 times pi over 4, a very simple integral. We just get a theta here evaluated at these 2 limits. So that's a very simple integral. And now, when we look here, this will give us 18 times pi over 4. And then, of course, we have 9/2 where we evaluated the upper and lower limits. That will give us a sine of pi and also a sine of 0. These both being 0. So when we reduce, we're just left with 9 pi over 2. Now, when you remember your techniques from Calculus 2, you were using a sector area formula. But the a double integral in the polar coordinates relieves us of having to memorize any formulas. The only thing we remember is the area element that we get from change of variables. So in actuality, this is a simpler calculation. One thing we don't forget is the methods that we learned in Calculus 2 using the Cartesian to get the actual polar equation. This technique is very useful, and again, you don't have to memorize anything. It's very easy to go from this graph to this graph as long as you respect the definition of r and theta in the polar plane. And we are done.